Okay, let's talk about analyzing and diagramming a mass spectrum. For more details on labeling the molecular ion, please see the other video I've posted on mass spec that talks about the nitrogen rule and how to detect chlorine and bromine, and the loss of water from an alcohol and isotope effects and all that good stuff for picking the molecular ion. It's the highest non-isotopic mass in your spectrum. What we're going to do, though, is we're going to focus on the major high mass. After we've labeled the molecular ion, we're going to focus on the major high mass peaks, and we're going to label those with their mass, the largest in a cluster, and we're going to ignore low mass fragments that are below the lower of one of the two, the lower of the half mass of the molecular ion or lower than the base peak. Whichever one's the lowest, we're going to ignore the fragments below that because they're likely fragments of fragments. And then we're going to label those fragments with how they differ from the molecular ion. So let's do an example right quick. So here's a spectrum, and we're going to label the molecular ion as the highest non-isotopic peak. So this, I don't see any evidence of chlorine, I don't see any evidence of bromine for the M and M+2. And let's look and see what this is. This is 86. Okay, very small carbon-13 isotope peak here that we can ignore. And then we've got major fragments. Are they odd or even? Well, 71, 60, or 59, 58. Okay, so there's an even. And then we have a 1, 2, 3, 43. So mostly odd and one even here that we have to take into account. Okay, so we've got an odd here and an even molecular ion. This would mean no nitrogen, but here is 86, so 43 would be halfway, and there's the base peak. So we're going to ignore everything underneath the base peak and consider only the upper ones. So here we have M-15, that's reasonable. Here we've got M-18, so if we added 18 there, or excuse me, 28 there, so 86, M-28. This should tell me McLafferty right here. That's an evidence of a McLafferty rearrangement, and that's something you can look at in the text and see McLafferty rearrangements. But then we have M-43 here as well. Okay, so 43 less than molecular ion. And so when we diagram it, we diagram not only what mass it is, but we diagram what we lose from that mass, and then we can venture a guess that this is loss of methyl, that this is loss of ethylene here, 28, and for 43 we can run a series of options here, but 43, 15 plus 14 is 29, plus 14 more would be minus a propyl group. So 28 and 15 would give us 43, so that could be loss of a propyl group right there. So we can venture a guess as to what we're missing. But that's how we diagram. Find the molecular ion, label the fragment masses. See these little ones here. They're not the highest in the group. We only care about the highest mass in the group in the high range of the spectrum. So we're analyzed and we're ready to go. Now what do? Well, we look for evidence of heteroatoms. We can use the IR. We can look for M-18, which is loss of water, indicating an OH or an oxygen in the compound. Methoxy would be M-, so oxygen weighs 16, methyl weighs 15, so 31 might indicate loss of a methoxy or an ethoxy here with 44, so we can look there. Easiest place to go for oxygen, though, is the IR. Look for a CO double bond, an OH, and something like that. Okay, chlorine bromine isotope effects we've talked about previously, none present here. Nitrogen, we can look at the IR for amines. We can look at the IR for a nitrile, but mainly we would look at the odd molecular ion for nitrogen. Okay, and we can then find the molecular formula by subtracting anything we found previously and divide the leftover by 13. So here I don't see any tremendous evidence of oxygen other than This tends to happen when McLafferty tends to happen when there's an ester or a ketone. So we might have an oxygen in there. Let's just start with what if it's all carbon and hydrogen. So what we're going to do is we're going to say, okay, our molecular weight, molecular ions, 86. Let's divide that by 13 and see how many C's and H's we can get. So we do that, 86 divided by 13, and we get 6 with a remainder. So that means C6, H6, and let's see what the remainder is. 13 times 6 is 78. 86 minus 78 gives us 8 left over. So plus 8 there. So our all carbon and hydrogen, one possibility for the molecular formula is C6H. 8 plus 6 is 14. Okay, so are we reasonable? And we have to decide that by calculating the degrees of unsaturation. And so the formula for that, as we've seen before in the isomers video, is 1 plus the number of carbons plus the number of nitrogens over 2 minus the number of things that bond once, like hydrogens and halogens, the sum of those divided by 2. So here we'd have that degrees of unsaturation is equal to 1 plus 6 minus 7 is 0 degrees of unsaturation. So that's reasonable. If we were negative degrees of unsaturation, that would be unreasonable. If we had more unsaturations than we had carbons, that would be very unreasonable to have for a compound, because if we remember, degrees of unsaturation are pi bonds or rings. So very difficult to have more pi bonds than we have carbons in a molecule overall, so, or rings for that matter as well. So we have no degrees of unsaturation according to the calculation if it is a hydrocarbon. But I'm going to tell you that there's evidence of McLafferty and evidence of a CO double bond in the IR. And so we need to account for one oxygen, and the way we're going to do that is we're going to say, well, let's exchange a CH4, which weighs 16, which is also the same as an oxygen. Let's exchange a CH4 for an oxygen. So I'm going to go C5, take away a carbon, take away 4 hydrogens, H10, and then give us an oxygen. That's going to weigh the same thing. It's going to weigh 86, and then we can see if this is reasonable. Degrees of unsaturation is equal to 1 plus 5 minus 10 over 2 is 5. That's 1 degree. Oxygen doesn't count. And if we saw a CO in the spectrum, that's very reasonable. Okay, something we could see. All right, so both of those would be reasonable, but because we saw evidence in the IR, we have C5H10O. We could say, well, 5 carbons should mean this is 5.5% of the height of the molecular ion, and that looks pretty reasonable. Hard to tell. We need exact values to check that, but that looks pretty reasonable. We could also explain the different peaks here, and I know what the compound is, and it turns out it's 1, 2, 3, 4, 5. It's 2-propanone, which would allow for a McLafferty rearrangement from this orientation to eliminate an ethylene M-28. So that is very reasonable for this mass spectrum here. Okay, and so we'll talk more about rearrangements and cleavage mechanisms in a different video. But that's how we generally analyze a spectrum. We go through our steps. We eventually we label everything with molecular ion, the high mass peaks, venture a guess at the fragments, and then we look at the evidence for heteroatoms in the IR and the fragment patterns and the isotope patterns. Then we find the molecular formula, the all carbon hydrogen, by dividing the molecular weight by 13, taking the remainder, and then we venture a guess at other heteroatoms by looking at the IR and our other evidences and seeing if they agree with each other. And when they do, if they are reasonable, we can look for more evidence in our spectrum, and we'll keep working examples to get better and better at it.